What are nuclear forces? Mention the characteristics or properties of nuclear force. Now, the strongest attractive force which binds the nucleons together is called as nuclear force. Before studying the properties of nuclear force, let us just concentrate on graph of potential energy versus the separation between the nucleons. Along x-axis we have r, which is the distance between the nucleons, and along y-axis we have potential energy in electron volts. We can see that as r is increasing, the potential energy decreases up to a value r naught, and after that the potential energy is increasing. R naught is about 0.8 Fermi, which is 0.8 into 10 to the power of minus 15 meters. From the graph, let us draw the properties or characteristics of nuclear forces. First, it is the strongest force in nature, which means the nuclear force are much stronger than gravitational force or electrostatic force. Second property is that it is a short range force in nature. Third, if the distance of separation between the nucleons is less than 0.8 Fermi or femtometer, the force is repulsive in nature. And if it is greater than 0.8 Fermi, the force is attractive in nature. This is something which we drew from graph. Okay, as potential energy starts decreasing, that is for value or for the distance of separation less than 0.8 Fermi, the force is repulsive in nature. But as the value or as the distance of separation increased from 0.8 Fermi, we observe that the potential energy has started increasing, which means the force is attractive in nature. Fourth point, nuclear forces are charge independent, which means that the forces between two neutrons, protons, or neutron and proton is same. It does not depend on the charge of the nucleons present. Fifth property, nuclear force have property of saturation. That means each nucleon interacts with only a finite number of nucleons around. A.H. Becquerel discovered radioactivity in 1896 accidentally. Becquerel considered some pieces of uranium potassium sulfate, illuminated light on them, and then wrapped them in black paper and separated the package from a photographic plate by a piece of silver. After several hours of exposure, the photographic plate was developed. It showed blackening. But what caused the blackening of photographic plate? The question was unanswered, and this led to discovery of radioactivity. So what is this radioactivity? The phenomenon in which a heavy element disintegrates spontaneously, emitting certain radiations, is called as radioactivity. There are three types of radioactive decays, namely alpha, beta, and gamma decay. We can see that alpha particles are attracted or deviated by magnetic as well as electric field. Similarly, beta particles are also deviated by magnetic and electric field, whereas gamma particles are neither affected by magnetic or electric field. Hence, we can say that gamma particles have highest penetrating or maximum penetrating property. Let us study in detail about alpha decay. As the name suggests, alpha decay has alpha particles. What are these alpha particles? Alpha particles are nothing but helium nuclei or atom. So we'll consider an example of uranium becoming thorium. Okay, so uranium 92-238 becomes thorium 90-234, emitting an alpha particle. In general, we can write parent nuclei as X, Z, A, which becomes daughter nuclei as Y, Z minus 2, A minus 4, plus with an emission of alpha particles. Here we can see clearly that atomic mass decreased by 2 and mass number has decreased by 4. Another example of alpha decay is radium becoming as radon with an emission of alpha particle. Q value or disintegration energy is defined as the difference between initial minus total mass energy. So initial energy is nothing but mxc square minus total mass energy is nothing but myc square plus mhe or m alpha c square. So when we substitute and calculate, we get our Q value as mx minus my minus mhe c square. Let us study beta decay. There are two types of beta decay. First, beta minus decay. Second, beta plus decay. Let us study about beta minus decay. In beta minus decay, a neutron gets converted into proton, giving out electron and antineutrino. Example, carbon 14 becoming nitrogen 14, giving out antineutrino plus electron. In beta plus decay, we can see that a proton becomes neutron, giving out positron and neutrino. Okay, example, carbon becoming boron. Here, one mark question can be asked. Why does a proton decays into neutron only inside the nucleus? Or why does beta plus decay occur only inside the nucleus? Answer is very simple, because the proton has smaller mass than neutron. Like an atom, nucleus also has discrete energy levels. Atomic energy levels have separation of about few electron volts, whereas in case of nucleus, the energy levels are of the order of mega electron volts. When a nucleus is in excited state and decays to its ground state, a photon is emitted with energy equal to difference in the two energy levels of the nucleus. This is called as gamma decay. So, when a nucleus jumps from its higher energy level to lower energy level, there is emission of radiations which have wavelength lesser than that of X-rays, and hence gamma rays are emitted in gamma decay. Gamma decay or gamma rays are emitted when alpha or beta decay takes place. Here we can see example of cobalt becoming into nickel. Okay. When cobalt undergoes beta minus decay and becomes nickel, nickel nucleus is still in excited state. So it gives out energy of about 1.17 mega electron volts and comes to a little lower, but still even there it is in its excited state. So it gives out excess of energy as gamma radiations or gamma rays of about 1.33 mega electron volts and then comes to its ground state. Now let us study a very important derivation. Okay, derive n of t is equal to n naught e to the power of minus lambda t, or derive an equation for number of particles at time t in a sample, or show that radioactive decay is exponential. These are different ways of asking question. Let us begin with our answer. Statement is very important and carries 1 mark. Statement is also called as radioactive decay law. So according to this law, the rate of disintegration of radioactive sample at any instant of time is directly proportional to the number of nuclei present in the sample at that instant of time. That is, dN by dt is directly proportional to n. Let us say there are n naught number of particles present at time equal to 0 and n number of nuclei present at time t. Dn be the number of nuclei disintegrating in time interval dt. Then we can eliminate our proportionality symbol by introducing a constant. That is, dN by dt is equal to minus lambda n, or dN by n is equal to minus lambda dt, where lambda is called decay constant or disintegration constant. Now, let us integrate the equation between the limits n naught to n and 0 to. Integration of 1 by n dn is nothing but log n. Lower limit and upper limit remains the same, that is from n naught to n, is equal to minus lambda is a constant, dt, integration of dt is t. Upper limit t remains as it is, lower limit is 0. Let us substitute the upper limit and lower limit in our given quantities. That is, log n minus log n naught is equal to minus lambda t minus t naught. We know the property log a by b is equal to log a minus log b. Using that property, we get log of n divided by n naught is equal to minus lambda t. When I want to eliminate log base e, I'll take log on the other hand side. So I get n by n naught is equal to e to the power of minus lambda t. Then I can write n is equal to n naught e to the power of minus lambda t, or n of t is equal to n naught e to the power of minus lambda. Radioactive decay constant. We know that n is equal to n naught e to the power of minus lambda t. Let us assume lambda is equal to 1 by t. Then we have n is equal to n naught e to the power of minus 1, or n is equal to n naught divided by e. 1 by e is equal to 0.37. From here, from this data which we derived, we will define radioactive decay constant. Radioactive decay constant is the reciprocal of the time during which number of nuclei of radioactive substance reduced to 1 by e times, or 37% of the initial number of nuclei. Half-life. Let us define half-life. Half-life of a radioactive substance is defined as the time during which the number of parent nuclei reduced to half of its initial value. Let us derive an expression for half-life. We know that n is equal to n naught e to the power of minus lambda t, where n naught is number of atoms or nuclei present initially in the sample, n be the number of nuclei present in the sample at time t, and lambda be the decay constant. T half is nothing but half-life of the sample. So I'll substitute T is equal to T half and N is equal to N naught by 2 in our equation. Therefore, I get N naught by 2 is equal to N naught e to the power of minus lambda T half. N naught and N naught gets cancelled. So I'll be left with 1 by 2 is equal to e to the power of minus lambda T half. I'll divide both the equations by 1. So I get 2 is equal to e to the power of lambda T half. I'll eliminate the exponential, so I can write ln of 2 or natural log of 2 is equal to lambda T half. Converting natural log into log, that is 2.303 into log base 10 of 2 is equal to lambda T half. Log base 2 is nothing but 0.3010. So 2.303 into 0.3010 is 0.693, which is equal to lambda T half. Let me just cross multiply. I get lambda is equal to 0.693 divided by T half, or T half is equal to 0.693 divided by mean life or average life of a radioactive substance is defined as the ratio of sum of lives of all the individual atoms to the total number of atoms present in the sample. Let N naught be initial number of atoms present in the sample, N be number of atoms present at time t, and Dn be the number of atoms undergoing disintegration between time interval t and dt. Let us say our time interval dt is very small, so t plus dt will be equal to t itself. We can assume that lifetime of each atom is equal to t. Sum of lifetime of all the atoms during disintegration in the time interval t plus dt is given as tdn. So we have just considered a small part of the sample where dn number of atoms are undergoing disintegration and their lifetime is given as dnt. But when we consider it as a whole sample, we can integrate between the limits n0 to 0 t d n. We know that dn by dt is equal to minus lambda n. So I can write dn is equal to minus lambda n dt, which I'll be substituting in my above equation. That is infinity to 0 t into minus lambda n dt. To eliminate the negative sign, I will reverse the integration. That is, I'll reverse the limit of the integration. So 0 to infinity t minus lambda becomes lambda because I have inverted the integration limits. Now I'll substitute n is equal to n naught e to the power of minus lambda t. We know that mean life is nothing but sum of the lives of all the atoms divided by number of atoms present in the sample. So tau will be equal to 0 to infinity t lambda n naught e to the power of minus lambda t dt divided by total number of atoms or nuclei present in the sample is n naught. Lambda and n naught are constants, so they come out of the integration. 0 to infinity t e to the power of minus lambda t dt divided by n naught. We know that when we integrate between the limits 0 to infinity t e to the power of minus lambda t dt, we get 1 by lambda square. So we substitute this in above equation. So tau is equal to lambda into 1 by lambda square, which implies that tau is equal to 1 by. When we see half-life and mean life, we can see decay constant is common in both. Hence, we'll derive the relationship between half-life and mean life. We know that half-life T half is equal to 0.693 divided by decay constant. We also know that mean life is equal to 1 by decay constant. When we compare equation 1 and 2, that is half-life and mean life, we get the relationship between them as tau mean life is equal to half-life divided by 0.693. Activity of a radioactive substance is defined as rate of decay at that instant. Decay rate or rate of decay is the number of nuclei disintegrating per unit time. That is, we can write both activity and decay rate A or R as minus dN by dt. We know that N is equal to N naught e to the power of minus lambda t. Hence, we get A or R is equal to minus dt of N naught e to the power of minus lambda t. When we differentiate it, we get A or R is equal to minus of minus lambda N naught e to the power of minus lambda t dt divided by dt. dt and dt gets cancelled. We get A or R is equal to lambda N naught e to the power of minus lambda t. We know that N naught e to the power of minus lambda t is nothing but N. Hence, we get A or R is equal to lambda N. There is another way of writing rate of decay. R is equal to lambda N naught e to the power of minus lambda t as R naught e to the power of minus lambda t, where R naught is equal to lambda N.